Okay, so now let's go ahead and start looking at some numbers and how we do these stoichiometry calculations. So we're going to start off by just doing some mole to mole, then we'll start adding in some grams and moles, and then we'll start doing grams to grams. Okay, so the key with these right here is we are just going to be looking at mole to mole right now. So when it says how much of for our product, we're just looking at moles because we're just going to compare moles to moles. So these will be easy. All right, so I have moles of hydrogen made from moles of hydrochloric acid. So our roadmap is we're going to go from moles of hydrochloric acid to moles of hydrogen. That's it. We don't have to do anything further because we can compare moles to moles. So we'll do our 3 moles of hydrochloric acid. Our balanced equation tells us we have 3 moles of hydrogen gas for every 6 moles of hydrochloric acid. So we'll get 1.5 moles of hydrogen made from every 3 moles of hydrochloric acid. All right, we've produced 4 moles of aluminum chloride. How much hydrogen? So again, we can do moles of aluminum chloride, 2 moles of hydrogen. Again, moles to moles. We don't need to do anything further. So I can do my 4 moles of aluminum chloride. And then my balanced equation tells me I have 3 moles of hydrogen for every 2 moles of aluminum chloride. Okay, so I'll get 6 moles of hydrogen. So for every 4 moles of aluminum chloride I produce, I can make 6 moles of hydrogen. All right, we're still working with the same example. So still moles to moles, we're going to go, this one wants us to go moles of aluminum, 2 moles hydrochloric acid. So if I have 1 mole aluminum, how much hydrochloric acid do I need to do the reaction? So 1 mole. Balanced equation says I have 6 moles of hydrochloric acid for every 2 moles of aluminum. All right, so we're going to get 3 moles of hydrochloric acid. So for every 1 mole of aluminum I react, I need 3 moles of hydrochloric acid. All right, now in the lab, do we weigh things out in moles? No, we weigh things out in grams. That's what our balances are for. So now let's start building some stuff in and looking at mass. So my first question here is I need to know moles of oxygen required to react with 50 grams of the CH4, methane. So we're going to go from grams of methane to moles of oxygen. Now, we can't do that. I can't go from grams of A to moles of B. I can only compare moles to moles. So I have to redo this roadmap and expand it and include another step. I can do grams of methane to moles of methane. And moles of methane can then go to moles of O2. So I have to go through moles. Now, I need to convert from grams to moles for my methane. How do we convert grams to moles? We use a molar mass. All right, so our molar mass of methane is 16.042 grams per mole. Remember, to get the molar mass, you're just summing the individual pieces up. So for this one, I would take my 12.01 for my hydrogen, or for my carbon, plus 4 times 1.008 for the hydrogen, and that's where we get the 16.042. Okay, so now I can solve my problem. All right, so we're going to do 50 grams of methane, 1 mole in our 16.042. And then we're going to do 2 moles of oxygen. That was weird. For every 1 mole methane. Okay, and we look good. My grams cancel, my moles cancel. I have moles of oxygen. Okay, and we end up with 6.23 moles of oxygen. Okay, all right, and that works on our significant figure level because I have 3 significant figures with my 50.0 grams of methane, so I have 3 significant figures for my moles of oxygen. All right, next up, we want to know the mass of carbon dioxide that we can produce by burning 6 moles of methane. So we're going to go from moles of methane to grams of carbon dioxide. All right, so can we do that? You're right, we can't. So we have to go from moles of methane to moles of carbon dioxide, and then we can go to grams. So moles of methane, moles of carbon dioxide, to grams. Okay, so moles to moles, we'll use our balanced equation, and then moles to grams, we need the molar mass. So for carbon dioxide, it's 44.01. All right, so we'll start with our moles of methane. Balanced equation tells us that we have 1 mole of carbon dioxide to 1 mole of methane. Even though the math is 1-to-1, we still have to show the step because we can't just convert numbers. We're converting the units too. So we still have to show the step even though it's 1-to-1. All right, and we get 264. Now, our moles of methane, 6.0. We only have 2 sig figs, so we're going to have to round this to 2 sig figs. So our 264, we can round to just 260 without a decimal point. That 0 is not significant, so we have 2 sig figs. Okay. All right, here is a similar one. All right, except now we got to write the balanced equation. So we have calcium chloride and silver nitrate. One of our products is silver chloride. So this is a double displacement reaction. So we need to not only write our equation, but we have to figure out what that other product is. So we have calcium chloride. We have silver nitrate. Okay, we're told that silver iodide or silver chloride is one of the products. Silver iodide we used in a lab. We're told that silver chloride is one of the products. We're given a gram amount, so we can surmise that that's our insoluble product. All right, and then what's our other product? Well, we have calcium and we have nitrate. We haven't used those 2 ions on the product side yet. So calcium nitrate would be our other product. All right, and then of course we have to balance it, and the balance on this one is a 2 there and a 2 there. Okay? All right, we're going to produce some silver chloride. We want to know how much calcium chloride we need to do that reaction. We have grams of silver chloride, so if we're going to do grams to moles, we're going to need a molar mass. So for our silver chloride, we're going to get 143.35 grams per mole. All right, so now we can solve our problem. We're going to go from grams of silver chloride over to moles calcium chloride. So again, I can't go from grams of A to moles of B. I have to go moles to moles. So I'll do grams of silver chloride to moles of silver chloride to moles of calcium chloride. All right, so we'll do our 6.60 grams, 1 mole in 143.35 And then our balanced equation, I have 1 mole of calcium chloride for 2 moles of silver chloride. So I'm going to get 0.0230 moles of calcium chloride. Okay? All right. Now, this is building us up to doing mass to mass. So, a couple of different ways we run reactions. Sometimes we have a concentration of an aqueous substance, and we can figure out stuff from there, and we'll talk about that at a different point. But the other thing is I have a balance in the lab, so I can mass out reactant, and then at the end I can mass out product. So that's where our mass to mass comes in. All right? So we've got this decomposition reaction here where ammonium carbonate is going to decompose into ammonia, carbon dioxide, and water. So let's write our equation. Okay, so we'll get our ammonia. We'll get our carbon dioxide. And we'll get our water. Okay? Next thing we have to make sure we do is balance our equation. And the balance on this one is a 2 in front of the ammonia. All right, so what we're doing here, we want to know how many grams of ammonia are formed from grams of ammonium carbonate. So we're going to go from grams of ammonium carbonate to grams of ammonia. And again, I can't do grams of one to grams of the other because they have different molar masses. So we have to go through moles. Okay, so there's our complete roadmap. In order to do these, we need 2 molar masses. We need the molar mass of ammonium carbonate and the molar mass of ammonia. So ammonium carbonate comes out to 96.094 grams per mole, and ammonia comes out to 17.034. Okay, all right, now I can solve my problem. All right, our balanced equation, we have 2 moles of ammonia for every 1 mole of the ammonium carbonate. And then finally, we've got that 17.034 grams per mole. All right, and so we end up with 0.177 grams of ammonia. Okay? All right. Now I want you to try this one. I'll go ahead and give you the equation on this one because this calcium cyanamide's a little weird. So your equation here is going to look like this. All right, so there's your equation. So we're going to do grams of calcium cyanamide, 2 grams of water. So write your roadmap. Okay, do you have your roadmap? Should go grams of calcium cyanamide to moles of calcium cyanamide, moles of calcium cyanamide to moles of water, and then moles of water to grams of water. So which 2 molar masses do you need? Think about that for a second. If you said you need the molar masses of calcium cyanamide and water, you were correct. So calcium cyanide's 80.11 and water is 18.016. Okay, and so hopefully you're solving, so try to set up the whole solution and see what you get. All right, so you should get this. And then our molar ratio. Okay, and then we get 50.6 grams of water. All right. Okay. Now, here's our last little bit. We're just going to do some mixed practice. So some might be moles to moles, some might have some grams, some might have some grams and moles. Okay, your balanced equation should look something like this. All right. Okay, so read this problem. All right, so this first one's just moles to moles. All right, when all is said and done, you should get 15 moles of oxygen. Okay. Same balanced equation. So this next one, you're looking at moles of copper 1 sulfide. You end up with some sulfur dioxide. So this one's a moles over to moles and then over to grams. And you should get 641 grams of sulfur dioxide. And then the last one, this one's in normal grams to grams. So grams of copper 1 oxide to moles, and then moles of copper 1 oxide to moles of oxygen, and then moles of oxygen to grams. And you should get 0.959 grams of oxygen, okay? So as I stress over and over and over and over and over again, you have to practice these problems, all right? You can't just copy what I write. You have to practice these problems, okay? So hopefully you're able to get those answers that I did on those last few.